So now the electrical engineers worry about these things, and what they do is they develop models as to how much signal will be received if I transmit from the antenna, and so that is called a channel model. And this is called a channel. This medium between the receiver and the transmitter is a channel. And received signal can be, now the thing is there are mathematical methods which require convolution, and you can do that basically convolution in time with multiplication in frequency. So this is the thing, and I don't need you to go to in this too much detail, but if you start doing research in wireless, or if you start working with people in wireless, like I have worked with people who are pure physics people or pure electrical engineer, then when they talk you have to understand, right? So basically then we need to know what this convolution is and all that. So basically anything, when you do convolution in time domain, it becomes a multiplication in the frequency domain and the opposite. So frequency and the time domain are always opposite. Okay, and we had talked about that the signal looks like an impulse in the frequency domain, but it is a sine wave in the time domain, and so on, right? So those things basically they just come naturally after you have done it a few times. So the signal X after propagation to the channel H becomes Y, where Y as a function of frequency. So you can plot it as a function of frequency. What is the power? YF. Y as a function of F is H as a function of F times X as a function of F plus N as a function of F. So everything is a function of F, but H is the channel model, X is the transmitted signal. So this is sent and this is received. So they basically multiply. Okay. So somebody can give you an HF, a formula for HF, and then if what you are transmitting, you know that. You multiply those two, you get the received signal, except that there is some noise on the way. N is the noise, which is added. So HF is the channel response, NF is the noise. Note that X, Y, H, N, all frequency, signal frequency, are all function of signal frequency. For example, the noise here is not equally distributed at all frequency. In some frequencies, there is bigger noise. Okay, so this noise clearly is a function of frequency, and the signal that I am sending is also a function of frequency. For example, I am speaking right now, it's not really a radio wave, but sound wave also same thing applies. Basically at some frequency there is a lot more power than other frequency. If a female starts speaking, the frequency shifts, as we talked about before, right? The frequency at which power is more is different, and so on. So every speaker actually has a different frequency. So path loss. So power is distributed equally into a spherical area of 4 pi d square. So basically when you send it, it goes in all the directions that we saw before. So the received power is proportional to the receiving area. So receiver is not going to collect the power from the whole sphere. It is going to have an antenna which could be, sometimes you have seen these parabolic antennas. If you drive by near NASA buildings, I don't know how many of you have, but basically not NASA building, even not NASA building. If you just drive by some big hotels, on the top they have these big antennas, right? Why they are big? Because they want to collect a lot of power. If they have a small antenna, then they will not get that much power, particularly if it is coming from the satellite. So basically, the farther the object is and you want to receive them, then you want to have a bigger antenna. So this is AR is the area of the receiver, PT is the transmitted power, GT is the transmitter gain, and 1 upon 4 pi d square is the area of the sphere. 4 pi d square is the area of the sphere, right? And so if you have an area AR, this is how much you will get. And now if you call the gain of the antenna as 4 pi upon lambda square AR, and this is what sometimes gets confusing, right? If you put GR equal to this, then you get this formula, and that's why I have to think for a minute as to why 4 pi is inside the square, because this is how the GR is defined. The gain of the antenna is defined 4 pi times lambda square, so 4 pi gets twice. D is already squared and lambda is already squared. So this was the previous formula we had seen before. PR is equal to PT, GT, GR, lambda upon 4 pi d square. And the reason, I mean, it is like this is because the antenna gain then doesn't depend upon the lambda. I mean, in this case, actually, it always depends upon the lambda. But basically, so that this formula comes out, this is known as Free's law, whatever, I don't know how they pronounce this name. But Free's law. And as you can see with this, lambda means wavelength, frequency on the bottom. Lambda is C upon F, right? C upon F is lambda. Speed of light divided by frequency is the wavelength. Right? If any of you have done the homework on number 3, which most of you haven't, if you had done, then you would remember that formula right away. C is equal to lambda upon F. Sorry, lambda is equal to C upon F. And C is equal to lambda times F. So anyway, so F would come out in the bottom. That means that the gain, the power will reduce as the frequency increases. That means the loss will increase as this frequency increases. So there are many things that I can ask. Power is the received power. When it decreases, the loss increases, right? Attenuation is loss with the frequency. So that's why high frequencies are not very good, right there. And that's why most of the world started with low frequencies. So we started with what we would call frequencies, and then we went to HF, high frequencies, and then when they got filled up, then we went to very high frequency, then we went to ultra high frequency, UHF, VHF, UHF, and then we said no, high, there's a mix, so we went on, and then now we are using, I don't know, there are no names for it, but basically now we measure it by gigahertz and terahertz and so on and so forth. Alright, so this is one thing we learned. But from this formula, it is clear that the attenuation increases with frequency. Is that clear to you? Yeah, right. So this formula is not for the attenuation, it is for the received power. So that's why I was confused for a minute, because with F being on the bottom, as the frequency goes up, the received power decreases. So the attenuation goes up.